Our guest today is Professor Bernard Widrow, one of the towering figures in the history of artificial intelligence research. Professor Widrow is Professor Emeritus in the Electrical Engineering Department at Stanford University, where he continues to carry on research on adaptive signal processing, adaptive control systems, adaptive neural networks, human memory, and human-like memory for computers. Among his many awards are the Benjamin Franklin Medal from the Franklin Institute, the Alexander Graham Bell Medal from IEEE, and the Hebb Award from the International Neural Network Society. He is a Fellow of IEEE, AAAS, and INNS, and a member of the National Academy of Engineering. So, very happy to see you looking so fit. Today, Bernie, and I'll begin just asking, how did you get into the field?
David, it's such a question. How did I get into the field? Well, let's see. I'll try to remember back how I first began with adaptive and learning. You know, I think when this all happened with me was I had just completed my doctorate at MIT. I was a student there, and then I became a faculty member there. I was at MIT for a total of 12 years. So I started as a freshman, and I ended up as a faculty member. When I completed my doctorate, just about to begin a 3-year appointment as an assistant professor. It was summertime. You see, you get your degree in June, so it was summertime. I was in a lab with a number of colleagues, and one of them, a man named Ken Shoulders, told me that there was a meeting going on at Dartmouth College that summer. This is the summer of 1956. And he said, there's a meeting going on at Dartmouth College on the subject of artificial intelligence. And I said to him, what's that? And he said, I don't know exactly, but it sounds interesting. Do you think you'd like to go with me? I said, sure, why don't we go? So he drove. We drove from Cambridge up to Hanover, New Hampshire. And the way this artificial intelligence conference, the way it worked was you come whenever you like, you leave whenever you like, you attend. If you want to say something, you raise your hand. If you don't want to say anything, you just want to listen, just sit and be quiet. You can do that too, whatever you wanted to do. And so we stayed for a whole week. I think the original pioneers were there. I can't remember exactly, but I'm pretty sure that Minsky was there, McCarthy was there, and probably Shannon was there, I'm not sure. I think von Neumann would have been there, except that at that moment he was deathly ill and just a very short time away from dying. And they were talking about building machines that would be intelligent, sort of like human intelligence. How can you automate human intelligence? And this idea sunk into my head, and it's still there. So I went back after a week, immersed in this, people talking about blah, 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 blah. Nobody having any idea how to do it, but sounded like a great idea. Everybody's got an idea, but nothing really you can sink your teeth into. I went back and started to think about thinking. How could you build a machine that thinks? What's thinking all about? So, you know, what exactly is going on in your head when you're thinking, when you're trying to solve a problem, for example? So I spent about 6 months thinking about thinking, came up with some ideas that I thought were well, today I think I was on the right track. Anyhow, it seemed to me then that in order to implement any of this with the hardware that we had available, it would be at least 25 years before anything could be done. And I had already gotten a taste of the academic life, and I liked it. And I knew that you couldn't keep working on something for 25 years and have nothing to report until 25 years into the future. This isn't going to work. Not only would it not work in academia, it would not work in industry or anywhere else. So the only way you could do that is to be independently wealthy, which I wasn't. In any event, I started to think, we're not going to be able to build a thinking machine. What can we do that would be interesting and having to do with thinking? Now, when my doctoral thesis, and remember I completed this in June of 1956. My doctoral thesis was on the subject of quantization noise. I became interested in quantization, round-off, and I began to study the statistics of round-off error. And this is something that crops up in all digital computation. Well, at the time I was doing this, there was hardly any digital computation, but I was interested in it anyhow. So I worked on that and finished in June with the doctorate. But what I had been teaching, I was teaching a graduate class when I was a graduate student. The graduate class, the subject was sample data systems. Today, you'd call that a mixture of digital signal processing and digital control systems, both. So I began to think about digital filters, and I was thinking, is there some way that the digital filter can automatically adjust itself to become a better digital filter? Can you automate that? In other words, let the filter design itself. So another way to say it is, can the filter learn from experience with working with input signals? And that's what I decided to work on, not try to build a brain or build a machine that thinks. In other words, to get something that does some elemental, simple form of learning, instead of trying to solve the whole problem all in one shot, is to pick a piece of it that one can do something about. And so there's a type of digital filter called FIR, Finite Impulse Response. What that is a tap delay line. And so you have an input signal coming in to a string of delays like Christmas tree lights, one right after the other. So that after the first delay, well, first of all, the signal is sampled in time. So you feed in a sample, that's the present sample. After a delay, you have the next sample. After another delay, you have the sample after that and so forth. So at the taps of the tap delay line, in other words, the joints between the delays, present signal, the previous signal, the signal from the time before that, before that, before that. And by taking those signals and weighting them and adding, making a weighted sum, you produce an output signal that's a linear combination of the present and the previous input signals. This is called a moving average filter. That's another way to call it, but in signal processing, it's called FIR, Finite Impulse Response. Now, to get an infinite impulse response, you have to have feedback. So this filter is feed forward, no feedback. Just the simplest digital filter I can think of. Now, how can you adjust the coefficients to make that filter become a better filter automatically? Well, what I did is a little bit of algebra, and I realized that regardless of the statistics of the input signal, that, well, wait a minute, I'm sort of jumping ahead. I need to tell you that one of the things that was studied in the class I taught on what was basically digital filtering was digital Wiener filters. And these are filters that are best linear least squares filters. So Wiener formulated a form of filter that if you know the input statistics, you can use Wiener's formulation. In other words, Wiener filter theory, to design the filter to optimize the impulse response of the filter so that you minimize the mean square error. Now, for example, if you had a filter that was, the purpose of it was to predict into the future. And I'll give you an example. Suppose you want to predict the stock market. A lot of people would like to do that. I wonder why. Anyhow, suppose that you had a record at the closing bell every day, what the Dow Jones average was. So you have today's Dow Jones close, and you have yesterday's Dow Jones close, and the day before's, and the day before that, and the day before that. You'd like to form a linear combination of those various closing values and use that to try to predict what tomorrow's closing Dow is going to be. So the simplest thing to do is just straight linear extrapolation. In other words, you take the present sample and the previous sample, you draw a straight line into the future, and that gives you an estimate of tomorrow, a guesstimate of tomorrow's Dow average. Now you can do something more complicated. You can fit a parabola to that, or you can fit a polynomial to the present and past inputs and make a best fit, and use that as an interpolator, an extrapolator, sorry. Wiener didn't quite do that. What he did is he found a way to design a filter, and in terms of, as we're talking about the Dow Jones average, how would you make a linear combination? How would you weight the present and previous samples of Dow Jones? How would you weight that in the best possible way to make a prediction of tomorrow's Dow Jones average, and do it with an error that's minimum in the least square sense? And what's the advantage of least squares? That means positive errors and negative errors are treated fairly equally. And so there are many other measures of error that you can have where positive and negative errors would be treated equally, like minimize the magnitude of the error, etc. But if you do it the way Wiener did, with minimum mean square error, it turns out that you develop Wiener filter theory that is an analytic theory, and you can do analytical work with a least squares criterion. And I think probably Gauss discovered this long before, and maybe Leibniz before him. So there's a long, long history of least squares. Wiener popularized it for filter design. Now, no one had ever designed filters before, digital or analog or whatever, that were optimal in the statistical sense, in the least squares sense. So Wiener introduced that idea, and I was teaching that to students as part of a class on digital signal processing and digital controls. So we were doing Wiener filter theory, not continuously like Wiener did, but we did it in the digital form, which is much, much simpler. If you do it with Wiener filter theory, the theory is based on calculus of variations. If you do it in the discrete, it's based on ordinary calculus. Everybody knows that. Well, I started working with this, and I realized that regardless of the nature of the input signal, other typical Wiener problems are not just prediction, but suppose that you have an input signal with additive noise, and you know the autocorrelation function of the signal, and you know the autocorrelation function of the noise, and you know the cross-correlation function between the signal and the noise. In other words, the signal and the noise are correlated. They spectrally overlap. Nevertheless, you're trying to design a filter that's the best possible linear filter to produce an output which is the best least squares estimate of the signal without the noise. Of course, any filter like that is going to let some noise through. It's not only going to let some noise through, but it's going to distort the signal in the process. But still, it's the best thing you can do to give you an output which is the signal without the noise. So the desired output, desired response, is the signal without the noise. Wiener introduced the idea of the desired response. Anyhow, the question is, how do you find the weights, the coefficients of this digital filter? And when I started doing some of the algebra, I immediately realized that for all the Wiener filter problems, whether it's noise filtering or prediction, or a mixture of both predicting and filtering noise at the same time, we were doing all that. The mean square of the error is precisely a quadratic function of the coefficients of the weights. So I began to imagine in my mind, draw pictures of a quadratic bowl. So you can draw a bowl, like a bowl shaped. And what you want to do is, if you start out with an initial guess as to what the best weight should be, you start out with an initial guess. So you're someplace up on the bowl. And what you want to do is to go down the bowl, down to the bottom of the bowl, where the mean square error is minimized. And where it's minimized, I call that the Wiener solution, named in honor of Wiener. So you want to find the Wiener solution. Well, how do you roll down the hill? You use the gradient. So that's what I started doing. And we began simulating this. I was at MIT, you know, for 3 years as a faculty member, and I began to have students. So I had a whole bunch of master students, and we started working on this. And we were simulating adaptive digital filters on an IBM mainframe. That was the only computer that there was an IBM mainframe. I think it was an IBM 701. I believe that's what the computer was back 1956, 1957, 1958. So we were simulating adaptive filters. The mean square error was, regardless of the nature of the input statistics, it didn't matter what it was, the mean square error was a quadratic function of the weights. So I started to do a little more algebra, and I realized, you know, if you write an expression for the gradient, if the mean square error is a quadratic function of the weights, then the gradient is the components of the gradient of partial derivatives of the mean square error with respect to these coefficients, the weights. And the gradient is a linear function of the weights, whereas the mean square error is a quadratic function, because, you know, if you take the derivative of a second degree, you get a first degree. We all know all that stuff. So the gradient was a linear function of the weights. So what I realized was that the method of steepest descent, which is what I was using, was really a feedback algorithm. And this was linear feedback. And what you had was the feedback was pulling the weights toward the bottom of the bowl. And going toward the bottom of the bowl, this is the objective. And the way we were getting the components of the gradient was by taking each weight and rocking it forward, measuring mean square error, rocking it backward, measuring mean square error, take the difference between the two mean square errors, and divide by how much you change the weight, and that gives you one component of the gradient. So you had to do this with all the weights to get all the components of the gradient. Now that you have a gradient, and it's never the true gradient, it's always an estimate because you're doing this with finite amount of data. You make a jump in proportion to the negative gradient. You make a jump in the weights. Now you're coming down in the direction of the gradient. That's steepest descent. So it turns out that you have transients in this feedback control of the weights. You're using feedback to control the weights, not to control the signal flowing through the filter. You're using feedback to control the design of the filter. And that feedback mechanism was steepest descent. Now, when you do it, you don't realize you're doing feedback. You don't realize anything. All you realize is that I'm finding the gradient. And once I have it, I make a jump in the direction of the negative gradient. Then I find the gradient again. I recompute it. In other words, run more data through the system and redo it, get a new gradient, make another jump and another jump and another jump, and keep on jumping until as you converge slowly, gradually onto the bottom of the bowl. So that's what we were doing. So we were making a filter basically that learns, and it learns from the input data. Now, when I was a graduate student, I took a class from a man named Y.W. Lee. Y.W. Lee was in electrical engineering. He was in the EE department. He was an electrical engineer from Tsinghua University. Norbert Wiener imported him from China. And he came to MIT and became Wiener's student. And Y.W. Lee was teaching Wiener filter theory in the electrical engineering department. There was no one in the math department is where Wiener was. Wiener was in the math department. Y.W. Lee was in the EE department. So you take Wiener filter theory as a EE class under Y.W. Lee, not under Wiener. Wiener wasn't teaching Wiener filter theory. He was busy with mathematics. And I have a suspicion about it, is that I don't, we hear all the scuttlebutt as students, because there are students in the math department, you're living in the dorms with these guys and you hear all the funny stories of what they were. And I think that what Wiener was doing, he also worked on Fourier analysis. Mathematicians are never really quite comfortable or happy with Fourier analysis for some reason. It's not rigorous enough, except it's incredibly useful. Well, it turns out that Wiener filter theory turned out to be useful, and if it has sort of the whiff or the threat of it being useful, then that's better for engineers rather than mathematicians. So I think that's why it was being taught in the EE department, not in the math department. Anyhow, the fear was that it could be useful. Well, it turns out it wasn't terribly useful the way I learned it. What we had was homework problems, Wiener filter homework problems. And what these homework problems were, here's a typical problem. Given an input signal with additive noise, given the autocorrelation function of the signal, the autocorrelation function of the noise, the cross-correlation function between them, design the optimal linear filter that will give you the best estimate of the signal so many seconds into the future. So in other words, you're doing prediction and noise filtering at the same time. Now this is really an ingenious thing to be able to come up with something like that. The only trouble with it is this was good for homework problems because they give you all these correlation functions for the homework problem. But when you go out in the real world, who's going to give you those correlation functions? Nobody. So how can you use this stuff? We don't. It's just of theoretical interest. But I always wondered when I was taking that class, what the hell do you do with it? Who's going to give you those correlation functions? So anyhow, when I started doing adaptive Wiener filters, we were not assuming that we knew the input statistics. All we had was input data. So it's a different way to go at what Wiener was doing. But without what Wiener had done, this never would have happened. So things develop, people learn step by step. Anyhow, we were working on that, and after a year or so, there was a master student who came to me, a man named Dick Mattson, and he was interested in doing logic, but doing logic with neural-like devices. In other words, they were a linear combiner where you take a combination of input signals and you go through a nonlinear device like a sharp quantizer. So the output is binary, one state or the other. So the input signals could be binary and the output signal is going to be binary, and the weighting coefficients in between adjust the logic. So he was interested in logical design. How do you design the coefficients? He came to me, I don't know how or why, but he was seeking supervision for a master's thesis. And I looked at what he was doing. I said, gee whiz, this looks just, this adaptive neural type element looks just like the adaptive filter. In other words, linear combiner is what's common to both. And so I became very interested in not designing the coefficients of a logic device that's based on neural type logic, but I became interested in how do you get those coefficients by a learning process. So here we were starting to do adaptation, making adaptive logic. And my friend Ken Shoulders was talking about pattern recognition. So I began to think about that. I said, you can put an input pattern into this logic device. If you can figure out how to train the coefficients, you can train it to make decisions based on the input pattern. And so we started doing that. So we were simulating a neuron on the one hand and adaptive filters on the other. We were doing both at the same time. Well, my three-year appointment was up, and I was being recruited by a man named John Linville to come to Stanford to join the EE faculty. So I went from MIT to Stanford, which was a very, very good move, it turned out. And why was that? Because an assistant professor at MIT had master students, but an assistant professor at Stanford had doctoral students. Quite a difference. You see, even in those days, the EE department at Stanford had a bigger doctoral student program than MIT did. Huh. And Stanford's EE department had 15 faculty. MIT's EE department had 60. So every subject of electrical engineering at MIT had several faculty in the same area, which is very nice. Stanford had in every area of electrical engineering one faculty member. So every man counts. They were all men. There weren't any women at that time. Today, it's a different story. We now have women on the faculty. And they're very, very excellent people. Dear ladies. Anyhow, so I came to Stanford, and I was sitting in my office one day, and I got a call from John Linville. And I have to tell you about John Linville. John Linville was half of an identical twin. The other twin was Bill Linville. Bill Linville was my thesis advisor at MIT. So this was kind of my getting to Stanford was kind of an inside job. You see, John Linville knew about me because I was a student of Bill for a number of years. Actually, Bill Linville was the one that founded that class in adaptive, in digital, not digital, what he called it was sample data systems, systems that had used sample data. The one who originated that was Bill Linville. That was the subject of Bill's doctoral thesis. So Bill left MIT and went to Washington, D.C. to work at IDA, the Institute for Defense Analysis. No one was there to teach the class in sample data systems. It was a very popular class. You had about 50 people taking the class. So I was there as a graduate student when Bill Linville left. And we continued with supervision of my thesis even after he was gone. But I started teaching that class. And that's how I was very, very familiar with digital filters. Not only having taken the class, but taught the class a year later. And that was a typical thing. You take the class, the next year you're an expert, you teach it. The first class I taught at MIT as a graduate student was called Principles of Radar. So I took the class, and the next year they didn't have anybody to teach it. So they said to me, "You want to teach that class? You know how to teach a class?" I said, "Sure, I know how to teach a class." Never taught a class before in my life. It was one of the best classes I ever had. The guys that had taken the class were all naval officers. This was right after the Second World War. And there were a lot of people in the military that were coming to MIT to complete their graduate education as part of their military service. So the guys in my class were all significantly older than me. They had been in the war, they had been out to sea, they had operated radar, they had experience with radar, and here I'm going to teach them about radar. Well, it turns out I knew the theory, they knew nothing about the theory, they knew how to operate the radar. So between us, we had a great time, and they were very, very serious students. They weren't a bunch of young puppies, they were serious grown-ups. And that was one of the best classes I've ever had. Anyhow, that's how I got started teaching principles of radar. How does a magnetron work? How do waveguides work? How do microwave antennas work? How do non-microwave antennas work? And all the stuff I learned about antennas turned out to be very, very useful later on in the development of adaptive signal processing. Everything.
You were about to get on to Stanford.
Yeah, I was teaching radar at MIT. And I got the time frames mixed up. In other words, that was a flashback. Just like in the movies, you have a flashback. I never liked flashbacks in the movies, but I did it to you. Anyhow, so we're now back at, I just gave you a little background about John Linville and Bill Linville and more stuff about how I got into teaching.
Yes.
It's sort of a side issue. So I was at Stanford minding my own business, sitting in my office, thinking about all kinds of stuff. And I got a call from John Linville. And he said, I've got this student, his name is Ted Hoff. And he said, I can't seem to get him interested in the research I'm doing. And what he was doing was he was doing research on semiconductor devices and transistor circuits. And Ted somehow didn't seem to get interested in that. So he said, look, Bernie, do you think maybe you'd like to meet with him? Maybe he would be interested in some of the things you're doing. I just can't seem to get him interested in what I'm doing. Would you like to see him? I said, sure. So the next day, was banging on my door is Ted Hoff. So he sits down and I get up at the blackboard. And what I was doing, explaining to him by drawing pictures and writing a little algebra on the blackboard of what I was doing. So I showed him about adaptive filters and how that ties in with an adaptive neuron. And I was showing him the quadratic bowl. I drew a picture of a paraboloid, because you can't do it in more dimensions than a paraboloid. And talking about the gradient, I showed him, derived the gradient and showed that it's a linear function of the weights, whereas the mean square error is a quadratic function of the weights. We were talking about the gradient, and somehow out of the discussion popped the idea that instead of taking a whole lot of samples of error, squaring them, taking the average to estimate the mean square error, and then doing it again and again and again as you rock the weights backward and forward. How about if you take a single sample of error, square it, and swallow hard because you're about to tell a lie. And the lie is, that's the mean square error. A single sample of error, square it, and say that's the mean square error. And you know this is not true. This is a very, very crude, noisy estimate of the true mean square error. But if you do it, you can work out algebraically what the gradient is in terms of the input data. You don't have to square anything. You don't have to average anything. You don't have to differentiate. You get it all algebraically with a couple of lines of algebra. So now we have a new way to get the gradient, an instantaneous gradient, highly noisy. So the only way to deal with a noisy gradient is to follow the negative gradient to go down to the bottom of the bowl, but take a very tiny step, and then take another tiny step and another tiny step. Well, it turns out, see, the idea is that this is averaging, and you're getting the effect by making small steps of getting an average. And it's like as if you average the gradient and took a bigger step. So you can take a lot of small steps, and that's averaging the gradient to average out noise, gradient noise. That's the idea of it. So we're following this crude gradient, and it was only years later that I sat down and wrote out the algebra, and I realized that this gradient is theoretically an unbiased estimate of the gradient. So in other words, the expected value of this crude gradient, the expected value of it is equal to the true gradient. Of course, you don't have the expected value. All you have is an instantaneous gradient. So by taking small, tiny steps, what you're doing is low pass filtering on the gradient. And the filtering is linear filtering because the gradient is a linear function of the weights. If you draw all this out, draw the picture, you'll see that steepest descent is feedback. And what you've got is linear feedback because the gradient is linearly related to the weights. So you got linear feedback. The gradient noise is like noise injected into a feedback loop. If you adapt slowly, the feedback loop acts like a one-pole, multi-dimensional, low-pass filter that filters out the gradient noise. That's the whole idea of the LMS algorithm. So now you've got a way of getting the gradient from a single sample of data, instantaneous gradient, putting that into steepest descent. The steepest descent says the next weight vector equals the present weight vector plus some coefficient, which we call mu. Some coefficient multiplied by the negative gradient estimate. And the negative gradient estimate was based on a single sample. So every time you get a new error sample, you make a small change in the weights. So you now have an iterative process that adjusts the weights with every new input sample, every new presentation of an input pattern. You change the weights a little bit, and then you repeat the patterns over again. And the best would be a random sequence, but you can do it cyclically if you like. It doesn't really matter much, as long as you adapt with very small steps. And then you slowly come down to the bottom of the bowl, and you get the Wiener solution, or close to it. Now, how close to it that you get depends on gradient noise. So the bigger steps you take in proportion to the gradient estimate, the quicker you get down to the bottom of the bowl. But the more noise propagates into the weights. So the noise in the weights means that you don't get down to the bottom of the bowl, but you undergo Brownian motion around the bottom of the bowl. So the fact that you're not at the bottom, but you're statistically around the bottom of the bowl, means you're rising up on the sides of the bowl, and you got more mean square error than you would have if you're always at the bottom of the bowl. So there's, on average, an extra mean square error. That extra mean square error divided by the minimum mean square error is a dimensionless measure of how close you are to the Wiener solution. The extra mean square error divided by the mean square error of the Wiener solution. How much more error do you have than the Wiener solution? Because you're never going to get the Wiener solution. That requires an infinite amount of data. That means you have to adapt infinitely slowly. If your boss wants you to adapt and you're telling him you're going to adapt infinitely slowly, he's going to say, you're fired. So you have to, you're working with a finite amount of data always. And that causes extra mean square error. Well, I gave a name to the ratio between the extra mean square error and the Wiener mean square error. That ratio I call the misadjustment. It's how much you're misadjusted. So I made up that word, I thought. Then I went to the dictionary and found out that, there actually is such a word as misadjustment. So it turns out to be a good word. It's a dimensionless measure. And misadjustment has sort of a dimensionless ring to it. So it's a measure of how close you are to Wiener. So what I found by experience is a design misadjustment of something like 10% is pretty good. You're only 10% worse than the Wiener solution, but you're going to be adapting at a pretty good rate. So if you adapt faster, let's say you can get, if you go twice as fast, you're going to get 20% misadjustment. If you go half as fast, you're going to get 5% misadjustment. So it's a trade-off between speed of convergence and the amount of misadjustment. Well, it turns out this works with neural networks as well as it works. And very few people really understand that. They just go ahead and play with it and set some rate of learning. But what effect does rate of learning have on performance, let's say, of a digital filter, an adaptive digital filter? So that's what I I worked all this stuff out. Eventually, I wrote a book on this subject called, what's the book called? Adaptive Signal Processing. It turns out that book was first printed in 1985. It's still in print. The book is selling better now than it did back in 1985.
Huh.
It still works. It's got all the stuff in it. And there have been at least 50 books on adaptive signal processing that have been written since. That one is the simplest, the most primitive, the easiest to understand. So if you really want a first book on the subject to learn what it's all about, that's the one. Then if you want to get into the fancy stuff, you have to get something more recent. As that field has developed over the years, it became a major part of the whole field of signal processing. So signal processing people, most of them are deeply into learning algorithms. Control people are not really into this yet, but we'll get them there.
Now you and Huff actually came up with a piece of equipment pretty soon after, didn't you?
We did. We came up with an adaptive neuron that we called Adeline, adaptive linear neuron, ADALINE. And actually, if you like, I've got one. I'm at home right at the moment, and what you see behind me is a picture. That's a lithograph by Roy Lichtenstein. And we've got all kinds of art here. You should see this house is like a mini museum of modern art. So that's been a passion of my wife and I. For years, we've been collecting fine art. And so we have quite a collection. On the other wall, you can't see it, but we got 3 screen prints by Andy Warhol and another very large picture by Roy Lichtenstein and all sorts of stuff. You'd be amazed.
Now,
so anyhow,
is that your laboratory?
Where I am now is down.
Right.
My house is built on a hill. The upper level of the house is at street level, and this is down below. Right outside on my right that way is a nice swimming pool. Because in California, you have to have a swimming pool. And what I'll do is I'll get up and go over in another part of this room. I'll get Adeline. Just a second.
Okay, great.
Oh, here's Adeline. I don't know if you can see it.
Yes, you need to prop that up. Put that in. Okay.
Let me see if I can put this down. Oops.
Okay.
No, that's the wrong way. It won't go far enough. I'll hold it up. You see it?
Yes, with a whole bunch of dials.
You see that what those dials are weights. The meter is reading the sum. So it's a linear combiner. And the dials, that we call them knobs. This is called knobby Adeline. Can you see it?
Yes, yes. And now, what year did you construct this?
This is 1960, I think. And if you look inside, you can see what electronics was like in 1960. This is a museum piece. This is all 1960 electronics. So let me describe this. It's hard for me to do it because I'm holding this up and I can't point to things. I need a box to put this up on. So these are the weights. The meter reads the sum. And let's see, I'm trying to figure out where, there it is. You see there's an array of switches?
Right, 16 switches.
Yeah, and there's a little window with neon lights. So whatever pattern you put in the switches, you can see the pattern in the lights. It tells you what you got. The switches are up or down, +1 or -1. So the inputs to the weights are binary. The weights are not continuous potentiometers, but they go like that, clickety clickety. And we did that deliberately so that when you're adapting it, you can decide how many clicks. So let me put it down. It's just, are we back again?
Yes.
The way it works is you put in an input pattern, and if you want the sum to be more positive, so you put in an input pattern and you know the desired response. You want that pattern to be classified as a +1 or a -1. Then you put in another pattern, you want that as, so you put in a pattern and you adjust the weights to cause the needle to read +1 or -1. So the meter has a scale, and on the right-hand side of the scale are positive outputs. To the left of 0 are negative outputs. The middle of the right-hand scale is +1. The middle of the left-hand scale is -1. So let's say you put in a pattern and the desired response is +1. So you put the pattern in, start out with, let's say, randomize the weights, put in an input pattern, present an input pattern, look at the sum. This is the weighted sum on the meter. And what is the desired response? Is it +1 or -1? Let's say it's +1. So whatever the needle is reading, you can bring the needle up toward the middle of the scale or bring it down toward the middle of the scale, if you wish, and adjust the weights accordingly. Now, if you add the pattern to the weight vector, add the pattern vector to the weight vector, that makes the dot product more positive. If you subtract the input pattern from the weight vector, that makes the dot product more negative. The meter is reading the dot product, the inner product of the two vectors, the input vector, the pattern, and the weight vector. So you're taking the vector dot product of the two and displaying that on the meter. So you add the pattern or subtract. Now, when you add the pattern, the input pattern is binary. So some of the inputs are +1, some are -1. So some of the weights, when you add that pattern, some of the weights will be increased, some will be decreased in accord with the input pattern. So what you're doing is you put the input pattern in, you look at the meter reading, and you see the difference between the meter reading and the desired response. And that's the error. But what you're doing is correcting the error. So you're going to add the pattern or subtract, add the input pattern to the weights or subtract it, depending on whether you want to increase the dot product or reduce it to get get the actual response closer to the desired response. You're trying to make the error smaller. So every time you adjust the weights, you're doing it to make the error smaller. So you add or subtract. Now, if the error is very small, you're getting almost what you want, but you still have an error. So then you add the input pattern to the weight vector. If you want to make the dot product more positive, and you do one click. In other words, you adjust, increase or decrease, increment or decrement the weights depending on the input pattern. And if the error were bigger, you give it 2 clicks worth. If the error were bigger yet, you give it 3 clicks worth. So you don't have to compute how much you're changing each coefficient. You just count the clicks. So you give it a round of clicks. And so you adjust all the weights and you do them one at a time. You do them all. And now you put in the next pattern and the next pattern. And then you repeat the patterns over and over again until the whole thing sinks in and it converges. Well, there's nothing that you can get that will let you examine how a learning algorithm works better than what Navier-Adeline does. You can see it, you can feel it. I've been using that Navier-Adeline for years and years to teach my classes. I always show the students Navier-Adeline. What I showed you is adding and subtracting the pattern vector from the weight vector in order to reduce the error. That's the implementation on the machine. But what that is exactly the same as what the algebra, when you write out algebraically, LMS algorithm. That is LMS algorithm, subtracted or added. That's LMS algorithm, and you do it in such a way to make the error smaller. So it's an error reduction algorithm, but it turns out that it's minimizing mean square error averaged over the training patterns. And it's minimizing mean square error, where the mean square error is the quadratic function of the weights. So that's Miss Adeline.
No, Bernie, I'd like us to be able to cover some of your major accomplishments and with a little maybe brevity. See, what are the things after Adeline that you're most pleased with that you were able to develop?
Well, when Hoffman, well, I'll just quickly finish up the story about the LMS. The name LMS, least mean square, that's not what Hoff and I called it in the first place. We didn't have any name for it. But a few years later, some of my doctoral students started calling it that, so the name stuck. Least mean square, LMS. Anyhow, when I wrote down LMS algorithm on the blackboard, within a half hour, Hoff had that up and running on an analog computer that happened to be located across the hall from my office. And we were so excited about what we were doing, we couldn't see straight. He went and programmed it. We were operating it, making it work. And the analog computer took up a whole room in the building. It was huge. So what we wanted was something small that could just sit on the desktop. So we decided we're going to build one. And it was a Friday afternoon, I remember. And by the time we decided we wanted to build something, it was late in the afternoon. The stock room, we had an electronic stock room where you can check out electronic parts, whatever you wanted. The stock room was already closed. And the next day was Saturday, so the stock room wouldn't open. We weren't going to wait for that whole weekend to go by. We couldn't, we were jumping up and down. So we went down to a local electronics store and bought all the parts. Hoff had some nice tools for metalworking and stuff. So we mounted the whole thing on an aluminum chassis and built up an Adeline. I had, on Monday morning, I had it so I can bring people into my office and demonstrate a learning machine. Never was there anything like that. Anyhow, the Adeline that I showed you was built about 6 months later by an electronic technician who had very great skill, and built it in a plastic case so you can see the insides. And it was good to have it in a plastic case, because I sometimes took it in the carry-on onto an airplane. When they started inspecting airplane luggage, they could look inside and make sure I wasn't carrying a bomb. See, if it were all aluminum and you couldn't see the inside, they would never let me on an airplane. Anyhow, so this went on. Hoff went on and did a doctoral thesis, and then he joined my lab as a research associate. And he stayed for a couple of years, doing all sorts of development of stuff in the lab, and maybe I'll have a chance to show you some of that. But anyhow, a few years later, it was a brand new company just getting started called Intel. And one of the founders of Intel was a named Bob Noyce. And Bob Noyce was a great friend and MIT buddy of Jim Angel, who was working with me in the lab. Some of his doctoral students were working with my doctoral students. They were all working together on learning stuff. And so Bob Noyce came to Jim Angel and wanted the suggestion, could he suggest somebody that they're looking for really smart people. Jim Angel says the smartest guy I know of who is now on the staff at Stanford is Ted Hoff. So they hired Ted Hoff away from me, but I told Ted, I said, Ted came to me and said, I got this offer, should I take it? I said, this looks like the greatest opportunity of your life. So he went to Intel. Eventually, within a short time at Intel, he started a project that developed the first microprocessor. So they gave it the name microprocessor. So he received the Kyoto Prize from the Emperor of Japan for the invention of the microprocessor. He receives from President Obama a Presidential Medal for Science and Technology. So that was my first doctoral student. He did well. He got Intel stock at the beginning, and I can tell you he's not hurting for cash. Okay. But he is one of the smartest guys I've ever known, is Ted Hoff. He knew everything. He knew chemistry, he knew physics, he knew mathematics. And after that, what else is there, right?
Now, in a few words, what are some of the other accomplishments of which you are most proud?
Well, I try not to be too proud. I have a nephew who is he's a physicist. He's teaching in Canada, actually, at Queen's College. His name is Larry Widrow. So my nephew, Larry, when he talks about stuff, his field is astronomy, astrophysics. And when they make a discovery, they get so excited. He says, it's exciting, it's exciting. I said, what the hell's exciting about it? It happened billions of years ago. What are you getting all excited about? So I try, I've done some things that I think have made quite a difference. Anyhow, the adaptive filter turned out to be one of the enabling technologies of the internet. See, the this kind of a filter that learns is used in equalization. The internet started with telephone channels. It wasn't wireless. It was all wired, and they were using the telephone system. The telephone system was designed for telephone calls, for voice. It's analog. It wasn't designed for transmission of high-speed digital data. So if you try to transmit high-speed digital data, you get a problem with the telephone line because the frequency of the phone line is not flat and it doesn't have sharp cutoff. If it did, you can transmit perfectly, because if you send an impulse into the phone line, like a digital impulse, if it were a perfect phone line, it would come out like through a low-pass filter. It would come out as a sync function at the receiving end. And if you transmit exactly at what's called a Nyquist rate, you can transmit so that a given pulse, see that a 1 would be a positive pulse, a 0 would be a negative pulse, +1, -1. You transmit a string of data pulses, some positive, some negative. You get a string of sync functions coming out at the receiving end, and if you did it just right, you'd be able to sense the output signal at the receiving end just at the peak of a sync function, and all the other neighboring sync functions would be having zero crossings. So you'd be able to pick out a particular sync function even though they're overlapping. That overlap is called intersymbol interference. So you can avoid intersymbol interference if the phone line were perfectly flat with an infinitely sharp cutoff. Now, a phone line, the frequency response is basically from 0 up to 3 kilohertz in a telephone line. And if it infinitely sharp cutoff and went all the way down to 0 frequency, the impulse response would be a perfect sync function, which would have a peak and perfectly uniformly spaced zero crossings. So if you get all the zero crossings of the neighboring pulses to come right at the peak of a particular one, you can tune in on the particular one and tune out all the other guys. So you'd be able to recreate the transmitted sequence perfectly without intersymbol interference. It turns out the phone lines are not perfectly flat. They don't have infinitely sharp cutoff, and they don't have linear phase characteristic. So what you want is a filter at the receiving end that can do the inverse of the phone line. So where the phone line has a frequency response peak, the filter wants to have a dip. Where the phone line has a dip, you want the receiving filter to have a peak. So the combination of the two, the phone line and the receiving filter, to give you pretty much this flat response, the beautiful sync functions. Well, it turns out that every phone line is different from every other. They're no two alike. What you need is something that can learn the characteristics of the particular phone line that you're using to do this inversion. And what you need is an adaptive filter. The adaptive filter was developed by Bob Luckey at Bell Labs. But Luckey was using the LMS algorithm to adjust the weights. So the LMS algorithm turned out to be an enabling technology, and now you have wireless links. They all have what's called multipath. They all have to be equalized. There's another thing that happens on a phone line with digital transmission. You get echoes because the phone line as a transmission line is not perfectly terminated. So you get echoes. So you have to have an adaptive filter to do echo canceling. So that this filter is clever enough to figure out what the echo is going to be and put an equal and opposite signal on the phone line to cancel that echo. So that's an echo canceller. So there are really two very important things done in digital transmission. Is equalization, in other words, flatten the response, linearize the phase, and at the same time, cancel echo. Both of these things are using adaptive filters with LMS or various forms of LMS. So without LMS, you wouldn't have the internet.
Hmm.
You and I wouldn't be talking to each other. Anyhow, so that's the little one thing that happened. So I guess the LMS algorithm is rather one of the key things that I can take satisfaction in, but also trepidation.
Huh.
Because whenever you develop something like that, you know that the good guys are going to use it, but the bad guys are using it too. The bad guys are going to kill us. Hopefully not. So that makes me worry. The other thing is, the next thing I was doing with adaptive filters was adaptive noise canceling. And how that came about was this. We were using adaptive LMS algorithm and adapting neurons, and we were building crude neural networks, like 2-layer networks. Adeline is an adaptive linear neuron. Madeline was multiple Adelines. So we have multiple Adelines, we called it Madeline.
Huh.
And Madeline, we were adapting that and we were using it for pattern recognition. We had a real-time, about 1961, 62, we had a real-time speech recognition system where you can train it with samples of your speech. And after you train it, then you can speak to it. And it types out on the computer's typewriter. It's an IBM mini computer in 1960 vintage. It would type out what you said. So we had a 10-word vocabulary. We were limited to 10 words in the vocabulary. We could do that quite reliably. But very, very crude network. We were quantizing the input, taking samples of the input signal, quantizing only to 4 quantum levels, because the analog to digital converter was all homemade. It wasn't something you can go in the store and get a card for your computer, which is a sound card with an analog to digital, digital analog, all this wonderful stuff you can do with 1,000 quantum levels or a couple of thousand quantum levels. We're using only 4 quantum levels and digitizing speech. But for a very limited vocabulary, it worked really well. Anyhow, so that's one thing we're doing, but this student was interested in electrocardiography. In other words, can you take electrocardiographic patterns and use it to diagnose various forms of heart disease? So he found a medical doctor named Joost van der Groven, who was in Stanford Medical School. And from van der Groven, he was able to get electrocardiographic data. So he was sampling electrocardiograms and feeding that in as patterns into Madeline and training it to do classification of various cardiac problems. Didn't work very well, but he did a nice doctoral thesis. Anyhow, that got me into medical problems. That's how, working with van der Groven, that got me started, and I worked with, probably over the years, at least a dozen faculty in the medical school on different medical problems that involved pattern recognition, control systems, all sorts of stuff. One of the problems we worked on was controlling of blood pressure in real time. In case someone had a, they come off the freeway with an accident, they come into the emergency room, they're in shock. How do you treat them? So you have various things that are infused. You have a drip, 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 an IV drip. How do you control the drip rate? At the moment, they use nurses that decide how many drops per minute according to what the doctor told her to do. So the doctor looks at the patient, senses what's going on with the patient, tells the nurse how many drops what we were doing is automatically figuring out what the drop rate should be in order to regulate the blood pressure. We were using experimental animals. We really did this. We were regulating blood pressure in real time on a big, giant German Shepherd dog. When the experiment was over, the dog came out of anesthesia. You had to anesthetize the animal because you can't take a German Shepherd dog and tie him down on an examining table. You use seatbelts to hold him down. You couldn't do that with a conscious dog. You have to give him something to knock him out, and then you can play with him, and then you wait until he starts to revive. When he gets revived enough, he's really screaming and yelling because he doesn't like being strapped down with seatbelts. You undo it and put him down on the floor. So his tail is wagging, all the students are there, so they start playing with the dog. And they forget all about their experiment. Anyhow, so these are some things that happened.
Okay.
So in other words, we worked on learning control, systems that learn. You have to learn the characteristics of that dog. Every dog is different. And we worked on adaptive noise canceling. And how I got into that was because of electrocardiography. Doctor showed me some electrocardiograms, and they were full of 60 hertz interference. In other words, the patient is on an examining table. You put electrodes on the chest and you're sensing the electrocardiogram. The trouble is the patient's body acts like an antenna picking up 60 hertz from the power lines all over the building. So you got 60 hertz interference. So he said, I'm now using a low pass filter that cuts off at about 50 hertz. So that it's about 30 or 40 dB down at 60 hertz. He was quite a good engineer. He was in the department of anesthesia, not cardiology. And anesthesiologists actually are technologists. They're practically engineers. What they explained this to me, that the surgeon is doing surgery on the patient. And every now and then the surgeon looks up, talks to the anesthesiologist, and he says, "How is the patient doing, doctor?" Because the surgeon has no idea how the patient is doing. The surgeon is busy doing the surgery. Whether the patient is alive or dead, the surgeon doesn't know about that. But the anesthesiologist sure as hell does. He's in charge of life support. The anesthesiologist's job is to keep the patient alive, but also keep him so he's feeling no pain. So you have to titrate the stuff you give him so that you keep him alive but keep him unconscious. Anyhow, so the working with electrocardiograms, Van der Groven said, what can we do about this? You see, I'd like to look at the electrocardiogram. I'd like to see a high fidelity electrocardiogram, not cutting off at 50 hertz. I'd like to go up to 150 hertz. So I think there might be some good information there that we're not looking at because of 60 hertz interference. So what can we do? I said, I have no idea. But you know, there was such a thing as a notch filter. But the trouble is that if you made a notch at 60 hertz, the power line frequency is 60 hertz, but that's only nominal. What I found out later is that it could vary plus minus a half a hertz or a hertz. What the power company wants to do is to get the number of cycles in a day to be a certain number of cycles so that everybody's electric clock will read properly. So if the frequency of the power system is going down, the power dispatcher will call up one of the power stations and tell the guy to put a little more coal on the fire. If they do that, that increases the pressure, the steam pressure, The turbine runs a little bit faster, and that pulls the whole system. See, it's all the generators are connected like with rubber bands. But when you understand electric machinery, you understand how that happens. It's like rubber bands. So they're all pulling toward each other, pulling each other up, pulling each other down, but they can't get out of sync. See, there's a limit to how much stretch. So if you call one power station and get it to increase the power, it'll go a little bit faster and it'll pull the whole system, pull everybody and raise it up. So they raise it up, lower it down. They're doing that all day long to try to keep the power line, but they don't, it's not perfectly 60 hertz. So a notch filter that's precisely 60 hertz can notch out the 60 hertz interference if it was 60 hertz exactly. What we developed was what amounts to an adaptive notch filter, that the notch tracks exactly the power frequency. And we did that by fighting fire with fire. So you have a patient on the examining table and electrodes on the chest, and you're sensing the electrocardiogram, but also you're picking up 60 hertz. Can't help it. So what my idea is, it took me a couple of years to figure this out. What my idea was, go into the electric wall outlet, pick up 60 hertz from the power supply, and take that, and if you can filter it just the right way, get the right magnitude and the right phase shift, you can combine it with the electrocardiographic signal and have it be equal and opposite to the 60 hertz interference mixed in with the electrocardiogram. And by doing that with LMSL weights, just 2 weights, you need 2 degrees of freedom because you're controlling magnitude and phase. You're not controlling that directly. You're controlling direct and a quadrature component of the power line signal. So when you do that, the thing adapts, converges, and learns. And boy, you can see an electrocardiogram like never before. And what I tell the students when they work with a doctor, we're all working together, make the doctor happy. That's your job. Make the doctor happy. Make it work. So we did that, and sometime later, let's say 1963, my daughter Debbie was born. Of course, this always happens in the middle of the night. So we got my wife to the hospital about 10 o'clock in the evening. They checked her in. And the daddies in those days weren't in with the mommies when they're having babies. They didn't allow anybody in there except the doctors and the nurses. So they checked my wife in, and I was sitting in the waiting room outside in the hallway. There were about a half a dozen daddies there. They were all there because their wives were having babies. And most of the guys were smoking, and everybody is very nervous. You know, you're nervous as hell. You don't know what you're going to get. You didn't know whether you're going to get a boy or a girl. This is 1963. And you didn't know, is the baby going to be okay? Is your wife going to be okay? You know, it's a risky thing. So what happened is I was sitting out there with all the nervous guys, myself being very nervous. This was my second baby, so I've been through it already once before. And a young resident came out in his doctor suit, you know, his white coat, and he's looking for me. Because when my wife checked in, he was asking her about family and stuff, and found out that I was outside and I'm professor of electrical engineering. And he had some electric station in the maternity wing of the hospital. and he thought maybe I'd be interested to see it. So he came out and got me and took me into inner sanctum where they don't let daddies. They had a whole bunch of labor rooms with ladies in labor. He had run a shielded cable going out to these labor rooms, and they put electrodes on the belly of the mother and can pick up signals from the heart of the baby. So you can see what's called fetal electrocardiogram. So he was back at the nurse's station. He had a rotary switch just like on Adeline. Click, 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 and he can click on different rooms with different ladies having different stages of labor. And what they're doing is looking to see if they can see get the heart rate. This was before they had ultrasound to get the fetal heart rate. They were using fetal electrocardiography. Well, the trouble is that you can pick up signals from the baby's heart on the belly, but you get a much, much stronger signal from the mother's heart. The baby's heart is teeny, teeny, weeny. The mother's heart compared to that is gigantic, even though the mother's heart is so far away from the belly where the baby is. The mother's signal is about 5 or 10 times higher in voltage than the voltage from the baby. So it's enough to create confusion that you can't really get a consistent reading of the baby's heartbeat. Now the baby's heart rate is roughly the order of 150 beats a minute. The mother's heart rate is the order of something around in there. The two heart rates are not synchronized. The baby's heart is beating independently of the mother's heart. So the question is, what can you do about this? So the doctor asked me this question. Yikes, yikes, yikes. What can you do? Well, the spectrum of the baby's heart, it's a little higher frequency than the mother's, but there's spectral overlap. The second harmonic of the mother is right smack in the baby band. Now, what the hell are you going to do? How are you going to separate this? I looked at it and scratched my head, and I have no idea. Well, we did, after that, we did the 60 hertz canceling, and students came to me sometimes looking for a research project, and I don't know what there was. I was thinking about fetal electrocardiography that day. There was something I read on the news about fetal electrocardiograms. I don't know what it was. And then they came in and asked me about what's going on, and I told them about canceling 60 hertz. And I said, you know, maybe wow, I got an idea. So here's the idea. Put electrodes on the belly of the mother to pick up baby, but you're picking up baby and mommy. Put electrodes near the heart of the mommy, chest electrodes on the mommy, pick up mommy loud and clear. And you're far away from the baby, and the baby is so small, you're not picking up hardly anything of the baby, just mommy. The mommy is the noise signal. You're going to filter that noise and subtract it from the signal on the belly, and you cancel out mommy and leave the baby. So we're able to do that, and you're getting baby loud and clear. So what the doctor we worked with that had the data where we had pregnant ladies, we took recording equipment to the hospital. I was there with the students. The students the students were all French students. There were 4 of them working with me. So the official language of the project was French. So you had a woman very pregnant on an examining table, and a screen, and one of the students on the project was a girl. So the girl student went on the other side with the doctor putting electrodes on the belly of the mother and then on the chest leads of the mother. And the boys and I were on the other side of the screen with the tape recorder. We were recording. We had a recorder that would go all the way down to 0. We had a very fancy Ampex recorder. And the weight, it was very heavy. It took 2 graduate students to carry it. Anyhow, we made the recordings and brought them back to the lab. And we were able to digitize them in the computer room and, on the computer simulate the adaptive filter. And we can subtract, use this to adaptively cancel the maternal interference and see the baby. And I tell you, we were quite pleased when we saw the result of that. We were able to take that and we had a digital plotter called CalComp. So we plotted it on the CalComp and we're able to take it up to back to the hospital and show the doctor. Boy, was he surprised. And so, we couldn't do this in real time. This was before you had like a laptop computer. Now you can do it with a laptop, do all this stuff with a sound card on the laptop and analog to digital, digital analog, do all the adaptive filtering on the laptop in real time, no problem. You couldn't do that then. But at least we established the way of how you do these things if you could. So the doctor was happy. So the students made the doctor happy. Everything was. Anyhow, the whole subject of adaptive noise canceling, how to fight fire with fire by adding noise to the noisy signal to eliminate the noise, to cancel it. But if you don't do it right, you can make things worse.
Huh.
You can't do it without an adaptive filter. It has to learn. It has to do it in using the adaptive feedback that does the control of the weights to filter the interference to create the canceling effect.
Bernie?
So you see noise canceling headphones, right?
Yes.
Well, that's a lot fancier noise canceling than what we were doing. But I came up with the idea of how to do that. That's really tricky because you're allowing the audio signal to go into the earphone at the same time that you're canceling the ambient noise. And this is much more tricky. It's really hard to get the noise signal all by itself. So it takes several adaptive filters working at the same time to make that work. But I published that result in a book. Sometimes I publish things at the patent office. Sometimes I publish things in the IEEE or in a book. That was published in a book. And so I think, it was in the public domain. I'm pretty sure I know exactly how these noise canceling headphones work. They won't tell you because all that is proprietary. But I know where they got it and I know what the heck it is. So noise canceling is one of the major things that I think I've had quite a lot to do. In other words, I'm the one that cooks up the idea.
Uh-huh.
My students finish it up and write doctoral theses on the subject.
Now, Bernie, you've had an extraordinarily long and productive career, but when I was at your place a few months back, I think you were still working on a book. So, what are you working on these days?
Well. It turns out I'm writing a book. I have to tell you, I'm 90 years old at the moment. And you say, what in the hell on earth is a 90-year-old guy doing writing a book? Well, I am. So I've been, I've got the body of a 90-year-old. I wouldn't mind having the body of a 30-year-old, but that's not going to happen. But I still have kind of the mentality of a kid. I never did grow up. People ask you, where did you grow up? And I say, I never grew up.
So what's the general idea for your new book?
The general idea is about 10 years ago, I became disaffected with neural networks. So this is before the convolutional network came into Google, and the whole field took off like a rocket. Before it took off like a rocket, it was really sort of, you know, we're doing it, we're having meetings, INNS, we have IJCNN, we do all this stuff, and no, it's fine. But I sort of started thinking more about how does things happen in the living system. Well, a few years after that, I was reading one of the IEEE journals. I forgot which one. And there were 2 articles in it where people were implementing Hebbian learning. They were making custom chips to do Hebbian learning. And I never was interested in Hebbian learning. You know, I was thinking, wire it together, wire it together. What the heck is that going to learn? This is ridiculous. This is nonsense. So I never paid much attention to it. But then I saw these 2 papers. These people are serious engineers, doing the work and writing papers and creating custom chips to do this. So I started thinking again about Hebbian learning. And I started reading some things about it, and you know, it's still wire it together, wire it together. Hebb didn't exactly say that, but that's basically the way people paraphrase it. And I just didn't know what to make of it. But I started thinking about it, and I began to think of what's wrong with it. What it does is it will only allow, fire together means fire together, wire together means if a presynaptic neuron is coupled to a postsynaptic neuron through a synapse, that if the 2 neurons are firing at the same time, that weight, the synaptic weight would increase. And what Hebb's argument was that if the firing of the presynaptic neuron is contributing to the firing of the postsynaptic neuron, then the postsynaptic neuron is successfully firing, the presynaptic neuron is contributing to the success. That this is a good thing. Let's let the coupling increase, and that's what nature is doing. But if the synaptic weights can only increase, then eventually all the synaptic weights will increase. They'll increase to saturation, and you'll end up with a stupid neural network, and this couldn't be. So there's more to it than what Hebb was talking about. But I think that Hebb introduced the idea that learning in the brain is associated with synaptic coupling change. He called the coupling the efficiency by which the presynaptic neuron influences the postsynaptic neuron. Now, the postsynaptic neuron has thousands of inputs, typically. Could have, typical is sort of 10,000 inputs to a neuron. And some of those inputs are excitatory, some are inhibitory. Well, what happens is that if you follow Hebb's learning rule, all the weights will eventually increase and increase and increase to saturation. And this is useless. There has to be some way that they decrease. So if fire together means that the weight increases, what I said, this is what I decided. If the presynaptic neuron is firing and the postsynaptic neuron is not firing, then that weight decreases. So if you follow Hebb's reasoning, if the presynaptic neuron is firing and it's unsuccessfully contributing to the, well, it's contributing, but it's unsuccessful and making the postsynaptic neuron fire, then the heck with it, make that weight decrease. So let me say it again. Wire together, wire together. But if the presynaptic neuron fires and the postsynaptic doesn't fire, then let them unwire together. Now, what Hebb was talking about was what's called an excitatory synapse. That means that signals coming into the excitatory synapse is the voltage of the nucleus of the postsynaptic neuron and contribute toward the firing of it. If the voltage of the nucleus of the presynaptic neuron is lower than minus 55 millivolts, that neuron doesn't fire. That's the firing threshold of human neurons. Minus 55 millivolts. How did nature come up with that? Who knows? But that's what it is. So minus 55 millivolts. So if you're below that, the neuron doesn't fire. If you're above that, the neuron is firing. Now, in the inhibitory synapse, for excitatory synapses, Hebb says fire together, wire together. So what I say is for an inhibitory synapse, the rule has to be the exact opposite. Because signals coming into the inhibitory synapse lower the voltage instead of raise the voltage. Lower the probability of firing, or if it's firing already, it'll lower the firing rate if you get an inhibitory input. Okay? Now, so fire together, wire together is good for inhibitory, but fire together, unwired together is what you have for, I mean, fire together, wire together is excitatory. Wire together, unwired together is inhibitory. Whatever the rule is for excitatory, it's the opposite for inhibitory. I just decided that. Nowhere in the literature could I find anything about it. You can hardly find anything about inhibitory synapses. Almost all the literature is excitatory. I think what happened is somebody started out initially like Hebb with excitatory, and the next person saw a paper written on excitatory and he's got some new stuff. So he does it for excitatory, and after that, excitatory and excitatory, and now 99 and 4400% of the papers are excitatory, and it's hard to find one on inhibitory. So I can make up any rule I want with inhibitory, and nobody's going to call me a liar. Anyhow, I'm just doing it based on simple reasoning, simple logic, based on the teaching of Hebb. Well, when you put this together for excitatory, inhibitory, wire together, but presynaptic fires, but postsynaptic doesn't fire, so then the opposite thing happens. And on the inhibitory side, the opposite again. You put all this together, you know what you get? LMS algorithm. So when I saw this, I said to myself, holy smoke. I'm beginning to get interested in heavy learning. And now I start reading and I find out more about how synapses work, how the electric chemistry works. You can do all this without going to the library. You can sit down at your computer and just use Google. Google will get this to you much quicker than going to the library and trying to figure out which library book you should take home. So Google will get you directly to an article that will tell you precisely the sort of thing you're looking for. But there's nothing you can find It tells you what causes the synaptic weights to increase or decrease. The only thing you got in the literature is Hebbian learning, which has to do with increasing the excitatory weights. But there's also the matter of decreasing the excitatory weights, and there's also the inhibitory weights. So I just rounded out the Hebbian learning in what I thought was the logical way, and the whole thing comes out to be LMS algorithm. Well, there are some experiments. Now I'm going to start talking neural net heresy pretty soon.
Oh, that's good.
We're going to talk about spike timing. Does that sound interesting?
Certainly.
Like to hear about spike timing? Well, in the various things reading, and in those IEEE article Hebbian chips that the guys were making, they also were talking about spike timing. And they point to a paper by two researchers that at the time Berkeley. Now, one of them was somewhere else. Their name, they had Chinese people, Chinese names, B.I. and Pu, P-O-O, B and Pu. So there were two papers written by B and Pu, and they had done some experiments in a petri dish. They had a neuron in an excitatory synapse in another neuron, and they had electrical pulse generators. And they were able, with external electrical pulses, to trigger the firing of the presynaptic neuron and the postsynaptic neuron. So the synapse is attached to the postsynaptic neuron. The other neuron is attached to it through its axon. In other words, the axon of the presynaptic neuron couples to the synapse into a dendrite of the postsynaptic neuron. So the coupling between them is the synapse. So they had a pulse generator where you can trigger the presynaptic neuron and make it fire a single pulse. And the postsynaptic neuron, you can trigger that and fire a single pulse. And they had a way to measure what the weight was. And they can measure changes in the weight as a result of. So you can do Hebb by firing the presynaptic neuron and firing the postsynaptic neuron, firing them both. This pulse generator they can control the spacing and time spacing between the two pulses. So their pulse generator put out a pair of pulses, and you can precisely control the timing between the two. So you can control spike timing between the presynaptic and the postsynaptic. What the B and Pu thesis was that the spike timing has everything to do with it. It has to do with whether you increase the weight or decrease the weight. What they said is, if the presynaptic neuron fires and then the postsynaptic neuron fires, the weight increases. But if the postsynaptic neuron fires first and then the presynaptic neuron fires, the weight decreases. So the weight decreasing is immediately way beyond anything Hebb was talking about. That's more like what I was talking about. What makes the weight decrease? Well, it turns out this is too complicated a story, but it's at the beginning of this book I'm writing. B and Pu interpreted this as spike timing has everything to do with increase and decrease of the synaptic weight. Now, what biologists call it is upregulation or downregulation. Upregulation means you're increasing the number of receptors. So the synapse has neurotransmitter and neuroreceptors. When you increase the weight, you increase the number of receptors. So in a synapse, the number of receptors increases or decreases. It upregulates or downregulates under control. What I'm saying is that the algorithm that's controlling that is an algorithm, a new algorithm that I call Hebbian LMS, Hebbian-LMS. What it is the extended Hebbian rules that I extended it. But those rules are verified by the Bee and Pooh experiments with living neurons and coupling. But there are different ways to interpret what Bee and Pooh did, but also they didn't go deeply enough in their experiment. And I can tell them what they can do to do their experiment that would prove that the spike timing is not what determines the increase and decrease of the weights. It's the Hebbian LMS algorithm that controls the increase and decrease of the weights. If you look at their papers, you can see that there are things that they didn't do that are left out. And when you take the theory developed with the Hebbian LMS theory, you do it, you get everything that they did plus stuff that they didn't do. When you add in the stuff they didn't do, you realize that what's controlling the regulation of the synapse, upregulate or downregulate, is Hebbian LMS algorithm, not spike timing. Now we got a whole slew of people doing research on neural nets, artificial neural nets with spike timing.
Oh.
Some people really believe in spike timing. They're able to make it work. Apparently, I haven't really followed it very well. But I don't think spike timing is the big experiments of Bee and Pooh. That if you just follow what Bee and Pooh says, you easily be persuaded that spike timing is what's doing it. But if you go further, deeper into those experiments, you find out that it isn't spike timing, it's something else. It just happens to be that as far as they went, the spike timing hypothesis works. But if you go a little deeper, that hypothesis doesn't work anymore. It's just like physics. You know, you got Newtonian physics, and that explains how the mechanical world works. Then along comes people doing experiments with very high speed and other things, and you find out that Newton's physics doesn't work exactly, and along comes Einstein, and he's got a theory that explains what the discrepancies are. That's what happens here. That the Hebbian algorithm fills in the gaps on the experiments done by Bee and Pooh. And when you fill in the gaps, you realize that the Bee and Pooh is very valuable experiments, but not enough to exhibit the failure of the hypothesis of spike timing. So it isn't spike timing, it's something else. It's extended Hebbian learning. And the extended Hebbian learning is LMS algorithm. But as I showed you with Adeline, the way we trained it initially, we were putting in an input pattern, we were telling it what we want the response to be. Suppose you feed in a pattern into Adeline and don't tell it what the response should be. Let Adeline tell you. In other words, do unsupervised learning with LMS algorithm. And the LMS algorithm that's involved in Hebbian learning is unsupervised, not supervised. You have something like 100 billion neurons in the brain. Each neuron has something like 10,000 synapses. So the number of synapses in the brain is 10,000 times 100 billion. It's lots and lots of trillions of synapses. Who's going to supply the desired response for training and controlling all those synapses? Where would that come from? Surely you must be joking. So it's to be unsupervised, I think. Anyhow, Hebbian learning is unsupervised, and Hebbian LMS algorithm is unsupervised. And when you build networks of Hebbian LMS neurons, they work, converge, learn beautifully. The individual neurons adapt and train all by themselves. It's not that they're all by themselves, they're all coupled together in the same network. It's just like cells in the body. Each cell in the body, in the human body, the animal body, or even trees and plants, each cell in the body is a little chemical factory. And it does chemistry all independently within the cell. But all the cells are connected together. They talk to each other. It's the same thing with neural cells in the brain. They all adapt and train independently of each other. They're all unsupervised, but they're all connected together. They talk to each other. An interesting thing.
Certainly is.
This is the basis of the whole book. Well, it turns out that with having an LMS theory, you can explain a lot of things. For example, how do opioids work? How do you get addicted? What do you do about it? What's depression all about? What's anxiety all about? What's bipolar disorder all about? How is that related to Hebbian learning? It is, I say. How is it related to the Hebbian LMS algorithm? That algorithm helps you to explain the subject of withdrawal with opioids because the weights have adapted. So it takes quite a while for me to explain it. I'd have to verbally explain the whole book to you.
I know you played a critical role in founding the International Neural Network Society. Could you describe some of the early days of the society?
Well, I can describe to you even earlier days yet before the society was formed. Stephen Grossberg is the founder of INNS, and he and I were in contact, and he said he wants to found a society. And I tried to discourage that. I thought that whatever we need to do in the field of neural networks, natural place to do it would be the usual, the IEEE. Well, it turns out that IEEE, you know, was a society that I kind of got born with and attached to. All my publications over all the years were almost completely in IEEE. And I told him I didn't see the need for it, but he insisted that he did. I said, okay, you're going to do it? Fine. Whatever help you need, I'll help you. And so that's how it happened. I was on the original board, and Steve was the president of the society. And we were all there at the beginning, trying to figure out what we should be doing. And it all worked out fine. Steve was president for a year. After that, I became president. I was president for 2 years. And after I was president for 2 years, they decided to put in term limits. So anyhow, it was a stormy period at the beginning. I was the one that was pushing for the conference called IJCNN. And Steve didn't like that idea, but I was president at the time, and the board was really supportive of trying to do something jointly together with IEEE. Because I thought IEEE is going to have a much bigger, let's say, broadcast appeal than we would be able to accomplish all by ourselves. And that was my thinking. this would be the best thing for the advancement of the field. I guess maybe I was thinking more of the field than anything else, and Steve was thinking of the society. And I thought that this would be for the good of everybody, everything. See, the society began to hold international conferences on neural networks every year, and the IEEE was doing the same thing. They were coming at different times of the year, about 6 months apart. So research people, they wanted to keep up with this, they had to go to 2 meetings a year. I thought if we can do it with 1 meeting a year, we're going to get a lot more people there, and just have a little bit longer meeting than we'd have if we had 2 separate meetings. And so that was the idea of IJCNN. And then we figured out how to make that work in negotiating with IEEE, that 1 year INNS would be the host. The second year IEEE will be the host, the organizer. So that's how that thing got rolling. And I guess it's been successful ever since.
Okay. What about for the present day? What do you think INNS should be doing?
I don't know, just don't have any specific ideas different from what's already ongoing. In other words, it's a society. Its purpose is research in artificial neural networks. And the only thing I can think of that might make sense for the society, actually would make sense for the field as a whole, is to extend, and Steve Grossberg was always trying to do this, is to try to relate biology to the artificial. And I think that this is something that could be emphasized more. And I think that, well, the research I'm doing right now is a mixture of biology and neural networks. And I think the research needs to go on in support of the big companies doing neural net research. They're going to need people constantly from now on. This field is not going to go away. This is truly another industrial revolution. Now, so the INNS needs to support that. But as far as research goes, I don't think individuals or faculty doing research in neural nets are going to be competitive against a company like Google that has billions of dollars to put into it, unlimited computer power, and thousands of workers working on the stuff. So I think go into an area where they are not for research. And I think the biological side, and I didn't get a chance to tell you in the last session about my own work on that, which is developing a learning algorithm, and I'm pretty sure is how learning takes place in the synapses of the brain. But what I didn't get to tell you is that same adaptive algorithm, the same learning algorithm, seems to be involved in the control of all the organs of the body. So you have adaptive neural networks all over the place. Just in the gut alone, the number of neurons in the intestines is of the order of 10% of the total number of neurons in the brain. So the gut is sometimes considered to be a second brain. It just doesn't do the same kind of thing as the big brain. So there are ways of studying adaptivity and learning in the body if you're using this to control the heart or control thermal regulation, which I've studied. The adaptive algorithm is mixed up with homeostasis. So wherever you have homeostasis, you got an adaptive algorithm. So the whole subject of adaptivity, not just learning. In the brain, you call this adaptivity learning. In the rest of the body, you call it messing around with hormones. See, the hormones in the body work just like neurotransmitters in the brain. And you have, in the brain, you have neuroreceptors. In the body, you have hormone receptors. They work very much like each other. And so this kind of study, it's a wide open field to try to understand and model physiologic phenomena all over the body. What I found is that this kind of learning algorithm helps understand things like mood disorders. So I guess I told you I'm writing a book.
Yes.
And one of the chapters is on addiction.
Oh, okay.
Opioid addiction. And it turns out that an adaptive algorithm has everything to do with the phenomenon of withdrawal. And what causes people to get addicted is that the withdrawal is so awful, you do anything to stop it. So the way you stop it is to take more drug. And once you're in that situation, you're hooked into it. And in order to get out of it, you have to go through withdrawal, which is excruciating.
Huh.
So I studied addiction, and I studied anxiety, depression, bipolar disorder. All these things involve neurons in the brain and how they work en masse. Not individual neurons and not little networks. These are big networks that have just an enormous effect over the emotional behavior of the individual. Know something about learning algorithms, how these adaptive algorithms work, is a great help in trying to understand these phenomena. And I can see that the biologists, they don't understand adaptivity. In other words, it's just not part of their sphere of thought. And that's something that we as a society could bring in. I could help. All you have to do is ask me. Now, I'm 90 years old, so you don't have all the time in the world. Anyhow, this book I'm writing has such a range of subject matter, I didn't know what on earth to call it. What kind of a title do you give a book that has to do with learning in the brain and adaptive phenomena and control systems that control the organs of the body? What do you call this thing? It also has to do with mood disorders. There's a chapter in this book, believe it or not, on cancer. Another chapter on viruses. Now, what can you call this thing? So
what kind of title did you decide on?
So I gave it a title. It's called Cybernetics 2.0. So in other words, it's like Wiener's cybernetics, where he talked about feedback control in the body, and man and machine is what he called it. So that's what this is, except that here we're getting into the nitty-gritty of how some of these phenomena that Wiener was talking about, how they actually work. What is the algorithm? See, when Wiener was alive, Wiener knew nothing about adaptive algorithms. They were just beginning to exist. The last time I saw Wiener was at a conference in Moscow in 1960. And he was so busy, everybody was all gaga over cybernetics. The Russians were just crazy about cybernetics. So he was celebrated as the big hero of the conference. He was it. And I saw him there. I could have had a chat with him because I had already developed with Ted Hoff, the LMS algorithm. I could have told him about that. But I could see, he's smoking a cigar and he's in his glory and he doesn't want to hear anything about anything. I know. And so I never really did talk with him and tell him about the future of Wiener filters. which are adaptive filters. In other words, filters that learn, but they converge on solutions that are best linear least squares, which he introduced. So he had everything except learning algorithm. He assumed for Wiener filters, the assumption is that why am I having a whoozy? That's probably because I'm 90 years old. Statistics, STA, don't ask me to spell it. Well, you caught me. Anyhow, he developed statistical methods of designing filters, which are called Wiener filters. But you have to know all the input statistics. You have to know the input autocorrelation function. If it's a noise filter, you have to know the cross correlation between the noise and the signal. You have to know all kinds of stuff. And then you can plug that into Wiener formula, come up with an optimal filter, and that's it. But what I was doing was working with filters where the statistics are unknown. Nobody's giving you the statistics. What they're giving you is input data. What you have to do is adapt from the input data to adjust the filter automatically. And you're using feedback to do it. And the feedback is controlling the parameters of the filter, not controlling the signals going through it. Up till that time, feedback was used to control signals. In this case, feedback is used to control the design of the system. And that's the key idea of adaptivity.
You know, I think you covered quite a bit of that last week, but now, and you're moving into sort of the next topic, which was what are people doing wrong or right in AI research now?
Well, I tell you, I'm too busy with the biological side of it and trying to understand biology to worry about what's going on at Google. But I do have spies there and keep up a little bit. But mainly what I find out about what's going on in the field is by reading the New York Times. So I read the New York Times every day. And I think they're doing fabulously. I don't know anything they're doing wrong. Everything they're doing is right. And what is it that they're doing? They're finding applications. And I'm not really sure whether they're using neural nets that are just deep in many layers, whether they're doing deep networks with convolutional techniques, convolutional neural networks. I'm not sure exactly which way they do it. They're not going to tell you anyhow. It's all proprietary. And my spies can't crack through the shell. So anyhow, I'm not sure I can give you a good answer to your question, but I give you sort of a general impression of what I think of it. And I think that the whole thing is unbelievable, what's happened. We could never in a million years have anticipated way back in the origins of the field exactly how this thing is going to develop. We knew we were into something that was quite significant, but we didn't have the horsepower to actually take on big problems. We couldn't do it. And, you know, we were there. The convolutional networks are mainly attributed to Kunihiko Fukushima. And I have to tell you that Fukushima was also on the first board of the INNS. So we were colleagues on the first board working together to try to make the thing work. And he was a very good colleague. I knew when I was president, I can always rely on him. And that gives you a little bit of story about Fukushima.
Okay, that's good. Do you have any advice to give for researchers just starting out in the field?
Well, the first thing you have to do is to study and try to learn everything that's known out there. It's all readily available. So study, study, study. But try to think for yourself what your own inherent interests are. And you'd be surprised that if you think about what would you like as an individual, what would you like to see? And you think you know, but you really don't.
Huh.
But anyhow, you have to start somewhere. And it's been so long ago since I started, you're asking me a question. You're really putting me on the spot. Trying to figure out how to advise. But you know, I've been a professor at Stanford for many years. I'm retired now 10 years ago. So I'm now 90. I retired at age 80. I was on the Stanford faculty in electrical engineering for 50 years.
Ah.
I was principal advisor for 89 PhDs. So I advised a lot of young people. But the thing is that when they became my advisee, they sort of fell into my orbit. And you know, they were looking to me for intellectual leadership. Now, you've got just thousands, maybe tens of thousands of young people who are young, beginning doctoral students who are in the field, both in electrical engineering and computer science. And I just, you know, if I could sit down with you, we can have a nice chat. I could really advise you, because I start asking you a lot of questions about what your background is like and what your interests are like. And before I would advise any of my students on what would be a good project for them to begin with, I would go through quite a bit of discussion with them about what kind of courses did they take? How did they do in these classes? Which classes did they like the most? What really turns you on? And when you get to know something like that, you're much better able to advise. Whenever a student would come into my office and he says, you know, I'm looking for a thesis advisor. What kinds of projects do you have? And I'll start telling them about what we're doing. And the student will say, gee, that sounds interesting. I wonder if I could become your doctoral student. I say, well, let's think about that. And then we sit down and have a big discussion about what interests you, what turns you on. And then I'll have some suggestions of directions of research. And you know, the student may like to pursue one of these, maybe yes, maybe no. But I've had a really large number of doctoral students. And so I've had a lot of experience at advising young people how to begin. But the other thing is that they get very strongly focused in areas where I was doing work myself. I always told them that the way to learn how to do research, there is no book on how to do research. There are no courses that teach you how to do research. The only way you can learn how to do research is to do research with people who are doing research, is to get involved with a research group, stick your nose into what they're doing, find out what everybody is up to, and see which direction would be of interest to you. And I would never tell a student you should do research on this and this subject. I would present an array of subjects that they ask me, well, what ideas do you have on different research subjects? So I would tell them what was on my mind, what are good directions to go in, what are things that we don't know about that would be useful if we knew. And they would be influenced by that, no doubt. But very often they would pick some topic, some subject that I would think is not the most fruitful thing that they could be doing. But I think it's most important to let the individual decide for him or herself exactly what they'd like to work on. I don't tell them what to do. Nobody told me what to do. As a matter of fact, well, I'll tell you a little bit of a story that this is related to, and I'll tell you why I don't tell people what to do. It happened in my own situation. I became very interested in the subject of round-off error, round-off noise, and digital computation. So I started working on trying to develop a theory of quantization. And I worked on that for about 6 months, and I came in and talked to my thesis advisor, and he said, Bernie, people have been working on quantization since man began working with numbers. And they haven't made a lot of progress with it. He says,
Bernie, I'm going to have to interrupt. Someone's at my front door. I'm going to pause, get right back to you.
But I'm going to tell you that after 6 months of struggling with this subject, I came to my advisor and we were just chatting, and he said, people have been working on quantization, trying to develop a theory of quantization noise, trying to do that since man first began to use numbers. And he said they haven't made much progress. One of the people who actually worked on that was Shannon. And so he said, I'm not going to tell you not to do this, but I'm just telling you that you could easily be going up a blind alley. The only trouble is I fell in love with the problem. And I was romantic and foolish. And I kept on and I found a way to crack it. Nobody had ever done it. I figured out how to use Nyquist sampling theory that you use on sampling signals. That's linear sampling to analyze quantization, which is a nonlinear operation. So I analyzed the nonlinear quantizer using linear theory. So how do you like that story? Now that was my first major piece of research. And I didn't have any trouble getting that thesis accepted. One of the persons who examined me when I presented my thesis, sort of what you call a thesis defense, was Jerry Wiener, who ultimately became president of MIT. So this was all at MIT, where I did all that. And then, thank God, I came to Stanford.
Okay, I think you've done a great job here. Any other comments you'd like to get on the record?
Well, I don't know whether I've answered your questions, but it's, you know, some of your questions are pretty difficult to try to give a general answer to.
Oh, sure.
So I
think you've done a good job.
I can only give you answers that relate to my own direct experience. And I guess I've had plenty of experience. I could tell you that when I first began in this field, the thing that got me started, I don't remember if I told you this already, but it was a conference at Dartmouth College.
Right.
And I became interested in developing a machine that can think. And that's what they were talking about. We still haven't got it.
Uh-huh.
And the developing this seemed to me to be very long term. So I knew all about digital signals, digital filtering. So I made a digital filter that was able to learn. Instead of trying to build a brain, I built a digital filter. And that's how we got started. Now, when I was doing that, I started on this in the year 1956. At that time, the number of people in the world that were doing anything like that was practically zero. And when I was doing all this work with students, after the first year or so, another student came to me with the idea of doing logic with a neural type logic element. In other words, an artificial neuron as a logic device. And I became interested in it because it had a lot of parts that were similar to the adaptive filter. So that's how I got started in neural networks, because the student brought this to me. And at the time, there were people at MIT that were working on artificial neural networks, the beginnings. There were Warren McCullough and a mathematician named Pitts.
Ah, yes.
McCullough Pitts. So they were at MIT when I was they were doing their stuff when I did simulated the first adaptive filters on the mainframe. I think it was an IBM 701 at MIT. But by the time after 3 years on the faculty at MIT doing this stuff, and then coming to Stanford, I was already pretty well into adapting, training a neuron and training an adaptive filter. And then I met Ted Hoff. But when we started doing work on neural networks, there were two people in Japan that were doing it, Nagumo and Noda. There was maybe one person in England, one person in Italy, maybe one person in Russia. And that was probably it for the whole world.
Huh.
So
not the story today.
That was the field of artificial neural networks. Also, I shouldn't forget, of course, Frank Rosenblatt at Cornell with the perceptron. And he made the biggest splash publishing a book called what the title of the book was, I don't remember. It was something neurodynamics, I think is what he called it. And then Minsky and Papert wrote the book Perceptrons a number of years later, doing everything they could in a very scholarly way. It was a very scholarly book, very well reasoned, very scholarly. But the only trouble is that their basic premises were off the track. And when you read the book and saw what they're aiming at and how easily it will be to get around their premises, you realize that what they were doing was a hatchet job on neural networks.
Huh.
And Minsky and McCarthy were the founders of the field of AI. I think it was McCarthy that invented the word artificial intelligence. They never developed artificial intelligence, not even close, nothing. And their biggest contribution was developing, popularizing the name artificial intelligence. And that process went on for years. You know, they had expert systems, and then they discovered, what do you call it? Oh, hell. Something else that sounds like subroutines. They discovered subroutines. Call them agents.
Oh, okay.
They had a big smear about agents. And what were they? Subroutines. And the expert system is just modeling human expertise. but not artificial intelligence. The thing was not intelligent on its own. It just trying to capture something of human intelligence, which is not a bad idea. And I was working on learning, and the people in AI had nothing to do with learning and nothing to do with neural networks. Neural networks was a dirty word in the field of AI. Did you know that?
I guess after Minsky.
Minsky and McCarthy. Not so much McCarthy. The one that made the most noise was Minsky. McCarthy was kind of a quiet little guy. He didn't make too much noise. But he came up with a programming language called Lisp.
Ah.
Everybody working on AI had to write in Lisp. Whether this is still used today or not, I don't know. But they were doing that. I didn't pay much attention to them because I thought that their book Perceptrons was just, the Minsky and Papert book was just nonsense. And it didn't stop us. But what it did do is stop a lot of government funding that might have gone into neural networks. So they succeeded in capturing DARPA. And DARPA put money into AI for years. Money, 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 money. Lots and lots of computer, lots and lots of this, that, or the other, but no AI. And then somehow or other, another group of people that was just not related to the original founders of INNS, but they sort of started with Terry Sinofsky.
Okay.
Terry Sinofsky decided he's going to make a journal, a new journal. And I talked with him. I tried to discourage him because I said, you know, there are enough journals out there already. What do we need another one for? But he said, no, we need a journal. Okay, so he made a journal. It was a great success. And that a conference at, where do they hold the conferences? I don't know, in ski country, wherever there's good skiing. You had to have a big conference. What they call that conference? What's the other big neural net conference?
Yeah, NIPS.
NIPS, that's it. The people at NIPS were the ones that really took over the mantle of AI. And they're the ones that got hooked up with DARPA and with, I don't know whether they really got any neural net money from DARPA. Because DARPA was pretty well inoculated against neural networks. And then the big companies got involved in it and put real horsepower into it. And they made it work. But I could have told you, I could have anticipated most of the applications that they're making of it. It was obvious, but we just couldn't do it. We didn't have the horsepower, you know, the originals. So I'd say the NIPS conference, coming from Terry Sinofsky originally, I think captured the mantle of AI. And AI soon forgot about expert systems and agents. They don't worry about agents. They worry now about neural networks, which is not learning. So the original AI had no learning in it whatsoever. So they're trying to build artificial intelligence without learning, which was ridiculous. They never did. They never did AI. And what we're calling AI now still is not AI. There's no intelligence. All these are trainable systems that can be trained to do very good things, and they generalize in a nice way. So that's what AI is now, is trainable neural networks. And what makes it a field of AI is, let's say you're trying to build a system for a self-driving car. So you have to be able to have something to look out the window and look at traffic signs, be able to read traffic signs, be able to see where the edge of the road is, be able to see where other traffic is. So you have to have a system that you can train with a semi-infinite number of different patterns that represent different situations. But the whole subject, you see, of getting a car to drive itself, you call that whole thing AI. AI is not just a neural net. It's the sensors, it's the actuators, it's everything to do with it. And how to combine all this together in a big system and make it so that it works and does something useful. That's what today AI is. But it's a long way from an artificial brain.
Okay, I think that we have enough material now. So I'm going to shoot this on over to Irwin King and see what his folks can do with it. But it's been great talking with you, Bernie. Now we're going to see how much progress you make on your book and see if you can get that book out the door.
Well, maybe I'll send you a copy.
I would like that.
If you'd like it, maybe you'd be a good guy to take a look at it. So you're a physicist. So you've got a very broad scientific background. And yeah, why don't I do that? If you can email me, send me your, well, I got your email.
Yes.
Yeah, I can email this to you. It's going through final editing.
Ah, great.
And
where's it being published?
I don't know yet.
Oh, okay.
I don't know yet. My last book was published by Cambridge University Press. So I don't know whether this would be a good book for them. The book on quantization noise was published by IEEE Press.
Hmm.
So they may be good people to do this. I haven't figured this out yet. I need to talk to some of my colleagues on the biological side, some of my friends in the Stanford Medical School.
Yes.
Who know how to get things out to people in that community. So I'm addressing this to people in the neural network community and people in the biology, bioscience, because what we're doing, it impacts all the biology. The only thing is that biologists don't know it yet. No, I'm not kidding. They just don't know. And I can tell when I read their stuff that there's something missing. And they don't know what it is. I think we can help. In other words, we need to collaborate with people in other fields.
Mm-hmm. Yes.
And that, I think, is the best advice I can give to young people going into the field, is to learn the basics and then start figuring out other areas where this has impact. I mean, I get things through Stanford Mail from all over the campus. So I know what's going on at the medical school. I know what's going on in the business school. The people in the business school are trying to use machine learning to establish protocols of how to run a business.
Uh-huh.
Makes sense. Can you use the computer in a way so that the chief executive can better run the company? And how do you develop that? And how do you teach it? So that these are other areas where the stuff we do impacts other fields. Start studying other fields that interest you and see how this basic stuff will impact those other fields. So,
very good.
So I don't know whether this is helpful. I think it's, I have to sit back and think about it. I think it's pretty good advice.
Yes. Yes. Well, it's been great talking to you, and be looking forward to hearing from you in the future, and hope everything works out well.